For the chapter objectives, students should be able to explain and differentiate different types of metal alloys, which is ferrous and non-ferrous alloy. Meanwhile, for lesson objectives, at the end of the semester, students should be able to apply and explain ferrous and non-ferrous alloys microstructure, strengthening mechanism and its applications, polymeric and advanced material structure, as well as its properties. Today we are going to look at on two topics, which is ferrous alloy and non-ferrous alloy. Well, basically, metal alloy by virtue of compositions are often grouped into two classes, which are ferrous and non-ferrous. Ferrous alloys, those in which iron is the principal constituent, include steels and cast iron. These alloys and their characteristics are the first topic of discussion for today's lecture. Meanwhile, for non-ferrous alloy, where all alloys that are not iron-based will be treated next. Yeah. So now let's look at on the overall content of the metal alloy. Ferrous alloys or ferrous metal, those in which irons is the prime constituent, they are produced in larger quantities than any other metal type. They are especially important as engineering construction materials. Their widespread use is accounted by three factors. Number one, iron-containing compound exists in abundant quantities within the earth crust. And number two, metallic iron and steel alloys may be produced using relatively economical extraction, refining, alloying, and fabrication techniques. Number three, ferrous alloys are extremely versatile in that they may be tailored to have a wide range of mechanical and physical properties. The principal disadvantage of many ferrous alloys is their susceptibility to corrosion. So in this lecture, we will discuss on the compositions, microstructures, and properties of the numbers of different classes of steels and cast irons. A taxonomy classification scheme for the various alloys, ferrous alloys, can be looked at from this diagram over here. Okay, so now let's move on to types of materials or alloys that falls under ferrous metals, which is cast iron. In general, cast irons are a class of ferrous alloys which with carbon contents above 2.14 weight% in practice. However, most cast iron contains between 3 to 4.5 weight% of carbon, and in addition with other alloying elements, of course. A re-examination of the iron-carbon phase diagram reveals that alloys within this composition range become completely liquid at temperature between approximately 1150 and 1300 degrees C, which is considered as lower than steel. Thus, they are easily melted and easily to be casted. Furthermore, some cast irons are very brittle, and casting is the most convenient fabrication technique. And cementite is the metastable compound, and under circumstances, it can be made to decompose to form alpha ferrite and graphite. The tendency to form graphite is actually regulated by the composition and rate of cooling. Graphite formation is produced or promoted by the presence of silicon in concentration greater than 1 weight%. Also, slower cooling rates actually during solidification favors graphitization or the formation of graphite. For most cast irons, the carbon exists as a graphite, and both microstructure and mechanical behavior actually depends on composition and heat treatment. The most common cast iron types are grey, nodular, white, malleable, and compacted graphite. So the list can be seen from figure A, B, C together with its microstructure for these types of cast iron. And for grey cast iron, grey cast iron the carbon and silicon contents actually varies from 2 to 4 weight% approximately of the carbon, and 1 to 3 weight% respectively for carbon and grey cast iron just now. For most of these cast iron, the graphite exists in the form of flakes, which are normally surrounded by alpha ferrite or pearlite matrix. The microstructure of a typical grey iron is shown in figure A over here. Because of these graphite flakes, a fractured surface takes on a grey appearance, hence it's become its name for grey cast iron. Meanwhile, for nodular or ductile cast iron, adding a small amount of magnesium or cerium to the grey iron before casting produces a distinctly different microstructure and set of mechanical properties. Graphite still forms, but as nodular or sphere-like particles instead of flakes. The resulting alloy is called ductile or nodular iron, and a typical microstructure is shown in figure B over here. The metric phase surrounding this particle is either pearlite or ferrite, depending on heat treatment. It is normally pearlite for cast piece. However, a heat treatment for several hours, about 700 degrees C, will yield a ferrite matrix, as in this photograph over here. Well, casting are stronger and much more ductile than grey cast iron. In fact, ductile iron has mechanical characteristics approaching those of steels. For example, ferritic ductile irons have tensile strength ranging between 300 to 400 megapascal. Ductility is from 10 to 20%. And the typical application for these types of materials include valves, pump bodies, crankshaft, gears, and other automotive and mechanical or machine components. Next is on white cast iron. For low silicon cast iron and rapid cooling rates, or most of the carbon exists as cementite instead of graphite. The fractured surface of this alloy has a white appearance, and thus it is termed white cast iron. So that's how the name being used for these types of alloys. And optical the photo micrograph over here, this one is figure C here, showing the microstructure of white cast iron. Okay, thick sections may have only a surface layer of white cast iron that was chilled during the casting process. Grey iron forms at interior regions, which cool more slowly as a consequence of large amount of cementite phase. White iron is extremely hard but also very brittle to the point of being virtually unmachinable. Its use is limited to application that necessitate a very hard and wear-resistant surface without a higher degree of ductility. For example, a roller in rolling mills. And generally, white cast iron is used as intermediary in production of yet another cast iron, like malleable cast iron or malleable iron. And heating white iron at temperature between 800 to 900 for a prolonged period of time in a neutral atmosphere causes a decomposition of a cementite, forming graphite, which exists in the form of clusters or rosettes surrounded by ferrite and pearlite matrix, depending on the cooling rate. The microstructure is similar to that of nodular iron, which accounts for relatively high strength and appreciable ductility or malleability. Representative applications include connecting rods, transmission gears, different cases for the automotive industry, and also flange, pipe fitting, valve, marine, and other heavy-duty services. Grey and ductile cast irons are produced in approximately the same amount. However, for white and malleable cast irons, they are produced in smaller quantities. Now let's move on to carbon steel. Steel or carbon steel that may contain appreciable concentrations of other alloying elements. There are thousands of alloys that have different composition and or heat treatment. The mechanical properties are sensitive to the content of carbon, which is normally less than 1%. Some of the common steels are classified according to carbon concentration, like low, medium, and high carbon steel. Subclasses also exist within each group according to the concentration of other alloying elements. Plain carbon steel contain only residual concentrations of impurities other than carbon and a little manganese. For alloy steels, more alloying elements are intentionally added in specific concentration. Now let's look at one by one. For low carbon steel, of all the different steels, those produced in the greatest quantities fall within the low carbon classification. These generally contain less than about 0.25% of carbon and are responsive to heat treatments intended to form martensite. Strengthening is accomplished by cold work. Microstructure consists of ferrite and pearlite constituent. As a consequence, these alloys are relatively soft and weak but have outstanding ductility and toughness. In addition, there are machinable, wettable, and of all steel, these types of carbon steel are the less expensive to produce. Example of applications include automobile body, component body, structural shape like I-beams, channel, angle iron, and sheets that are used in pipelines, building, bridges, and tin cans. Another group of low carbon alloys are the high strength, low alloy HSLA steels, they call it. They contain other alloying elements such as copper, vanadium, nickel, and molybdenum in combination concentrations as high as 10% and possesses higher strength than the plain carbon steels. Most may be strengthened by heat treatment, giving tensile strength atmosphere. The HSLA steels are more resistant to corrosion and the plain carbon steel, which they have replaced in many applications where structural strength is critical. Hold on, yeah. Okay, so let's continue with medium carbon steel. I think for this slide, I just summarized a little bit on medium carbon steel because the most important part is the low carbon steel and high carbon steel. Anyway, for medium carbon steel, the concentration of carbon is between 0.25 and 0.6 or 0.3 or until 0.6 weight percentage of carbon. These alloys may be heat treated by austenizing, quenching, and then tempering to improve the mechanical properties. They are most often utilized in the tempered condition, having microstructure of tempered martensite. The plain carbon steels have low hardenabilities and can be successfully heat treated only in very thin sections and with very rapid quenching rates. Additions of chromium, nickel, and molybdenum can improve the capacity of this alloy to be heat treated, giving rise to a variety of strength ductility combinations. These heat-treated alloys are stronger than the low-carbon steel but at a sacrifice of ductility and toughness. Applications include railways, wheels and tracks, gears, crankshaft, and other machine parts, and high-strength structural components, calling for a combination of high strength, wear resistance, as well as toughness. So let's move on to high carbon steel. The high carbon steel normally the percentage of carbon content is more than 0.6 weight percentage of carbon. They are the hardest, strongest, and yet least ductile of the carbon steel. They are almost always used in hardened and tempered condition, such as wear resistant and capable of holding a sharp cutting edge. The tool and dies are high carbon alloys, usually containing chromium, vanadium, tungsten, and molybdenum. These alloying elements combine with carbon to form very hard and wear resistant carbide compounds. These steels are utilized as cutting tools and dies for forming and shaping materials, as well as knives, razors, hacksaw blades, springs, and high strength wires. The stainless steel are highly resistant to corrosion in a variety of environments, especially the ambient atmosphere. Their predominant alloying element is chromium. A concentration of at least 11% of chromium is required. Corrosion resistance may also be enhanced by nickel and molybdenum additions. Stainless steel are divided into three classes on the basis of predominant phase constituent of the microstructure, which is martensite, ferrite, and austenite. Martensite stainless steel are capable of being heat treated in such a way that martensite is the prime microconstituent. Additions of alloying elements in significant concentration produce dramatic alteration in iron carbide phase diagram. For austenitic stainless steel, the austenite phase field is extended to room temperature. Ferritic stainless steels are composed of ferrite, alpha ferrite, alpha ferrite phase. The austenite and ferritic stainless steel are hardened and strengthened by cold work because they are not heat treatable. The austenite stainless steels are the most corrosion resistant because of high chromium contents and also high nickel additions, whereby they produce in the largest quantities. Both martensite and ferritic stainless steels are magnetic. The austenite stainless steels are not. Some stainless steels are frequently used at elevated temperatures and in severe environments because they resist oxidation and maintain their mechanical integrity under such conditions. The upper temperature limit in oxidizing atmosphere is about 1000 degrees C. Equipment employing these steels includes gas turbine, high temperature steam boilers, heat treating furnaces, aircraft, missiles, nuclear power generating units, and so on and so forth. Now let's move on to non-ferrous alloy. Steel and other ferrous alloys are consumed in exceedingly large quantities because they have such a wide range of mechanical properties, may be fabricated with relative ease and are economical to produce. However, there are some distinct limitation. Includes number one, a relatively high density, comparatively low electrical conductivity, and number three, it has an inherent susceptibility to corrosion in some common environments. Thus, for many applications, it is advantageous or even necessary to use other alloy than have more suitable property combinations. Alloy systems are classified either according to the base metal or according to specific characteristics that a group of alloys can share. So in this topic, we will discuss the following metal and alloy system, which includes copper, aluminium, magnesium, and titanium alloys, which also includes the refractory metals, refractory materials, I think, for this section. So now let's move on to first types of non-ferrous alloy, which is aluminium. Aluminium and its alloys are characterized by a relatively low density, have high electrical and thermal conductivities and resistant to corrosion in some common environments, including the ambient temperature. Many of these alloys are easily formed by virtue of high ductility. This is the evidence by thin aluminium foil sheet into which the relatively pure material may be rolled. Because aluminium has FCC crystal structure, its ductility is retained even at very low temperatures. The mechanical strength for aluminium may be enhanced by cold work and by alloying. However, both processes tend to diminish resistance to corrosion. Principal alloying elements include copper, magnesium, silicon, manganese, and zinc. Non-heat treatable alloys consist of single phase, for which an increase in strength is achieved by solid solution strengthening. Others are rendered by heat treatable as alloying, as a result of alloying. Generally, aluminum alloys are classified as either a cast or wrought. Composition for both types is designated by 4-digit numbers that indicates the principal impurities and in some cases the purity level. For cast irons, a decimal point is located between the last 2 digits. After these digits is hyphen, and the basic temper designation is like a letter and possibly a 1 to 3 digit number, which indicates the mechanical or heat treatment to which the alloy has been subjected. For example, it has a H, F, or O represent respectively as fabricated, strain hardened, and anneal states. T3 means that the alloy was solution heat treated, cold work, and then naturally aged. Some common example or applications for aluminium's alloy includes aircraft structural parts, beverage cans, bus body, and automotive parts, and so on and so forth. Number 2 is copper alloys, or copper and copper-based alloys possessing a desirable combination of physical properties have been utilized in quite a variety of applications since antiquity. An alloyed copper is so soft and ductile that it is difficult to machine. Also, it has an almost unlimited capacity to be cold work. Furthermore, it is highly resistant to corrosion in diverse environments, including the ambient atmosphere, seawater, and some industrial chemicals. The mechanical and corrosion-resistant properties of copper may be improved by alloying. Most copper alloys cannot be hardened or strengthened by heat treating procedure. Consequently, cold work and solid solution alloying must be utilized to improve these mechanical properties. The most common copper alloys are brasses, for which zinc as a substitutional impurities is the predominant alloying element. Some of the common brasses are yellow, naval, cartridge brass, and gilding metal. And the examples include, the applications include custom jewelry, cartridge castings, automotive radiators, musical instruments, electronic packaging, coins, and so on and so forth. The bronze are alloys of coppers and several other elements including tin, aluminium, silicon, and nickel. These alloys are somewhat stronger than the brasses, yet still have a high degree of corrosion resistance. Number 3 is the magnesium alloy. Perhaps the most outstanding characteristic of magnesium is its density, which is the lowest of all the structural metals. Therefore, its alloy are used where lightweight is an important consideration, like in aircraft components. Magnesium has HCP crystal structure. It is very relatively soft and has a low elastic modulus. At room temperature, magnesium and its alloy are difficult to deform. In fact, only small degree of cold work may be imposed without annealing. Consequently, most fabrication is by casting or hot hot working at temperatures between 200 to 250 degrees C. Magnesium, like aluminium, has a moderately low melting temperature. Chemically, magnesium alloys are relatively unstable and especially susceptible to corrosion in marine environments. On the other hand, corrosion or oxidation resistance is reasonably good in normal atmosphere. It is believed that this behavior is due to impurities rather than being an inherent characteristic of magnesium alloys. Fine magnesium powder ignites easily when heated in air. Consequently, care should be exercised when handling in this kind of state. These alloys, magnesium alloys, are classified into either cast or wrought, and some of them are heat treatable. Aluminium, zinc, manganese, and some of the rare earths are the major alloying elements. A composition temper designation scheme similar to that of aluminium alloys is also used. Furthermore, in the last several years, the demand for magnesium alloys has increased dramatically in a host of different industries. For many applications, magnesium alloys have replaced engineering plastic that have comparable densities, in as much as the magnesium materials are stiffer, more recyclable, and less costly to produce. For example, magnesium is now employed in a variety of handheld devices like chainsaws, power tools. Meanwhile, in automobile like steering wheels, columns, frames, transmission cases, and in audio visual camcorders, TV sets, cellular phone, laptops, computers, and so on and so forth. Now let's move on to next materials for non-ferrous alloy, which is titanium and its alloy, whereby these types of materials are relatively new engineering materials that poses an extraordinary combinations of properties. The pure metal has a relatively low density, high melting point, and elastic modulus of 107 gigapascal. The titanium alloys are extremely strong. Room temperature tensile strength can be as high as 1,400 megapascal. They are attainable, yielding remarkably specific strengths. Furthermore, the alloys are high ductility, having high ductility and easily forged and machined. The major limitations of titanium is its chemical reactivity with other materials at elevated temperature. This property has necessitated the development of non-conventional refining, melting, and casting techniques. Consequently, titanium alloys are quite expensive. In spite of this high temperature reactivity, the corrosion resistance of titanium alloys at normal temperature is unusually high. They are virtually immune to air, marine, and a variety of industrial environments. They are commonly utilized in airplane structures, space vehicles, and surgical plants, and in the petroleum as well as chemical industry. Last but not least is on the refractory materials. Metals that have extremely high melting temperatures are classified as the refractory metals. Included in this section are niobium, molybdenum, tungsten, and tantalum. Melting temperatures ranging between 2468 degrees C for niobium and 3410 for niobium. The highest melting temperature of all metal for tungsten, with the value of 3410 degrees C. Interatomic bonding in these metals is extremely strong, which accounts for the melting temperatures, and in addition, large elastic moduli and high strength and hardness at ambient as well as elevated temperatures. The application of these metals are varied. For example, tantalum and molybdenum are alloyed with a stainless steel to improve its corrosion resistance. Molybdenum alloys are utilized for extrusion dust and structural parts in space vehicles. X-ray tubes and welding electrodes employ tungsten alloys. Tantalum is immune to chemical attack by virtually all environments at temperatures below 150 degrees C and frequently used in applications requiring such as corrosion resistant materials. So that would be all for today's lecture. I hope everybody do understand what are the topics being delivered to you, being taught for today. However, if you still have any question related to the topics, you may contact me in a group or in a WhatsApp group or in Google Classroom. And that will be end for our chapter 6 for this chapter. So in the next class, we are going to look at a new chapter, which is chapter 7. And that would be all for today's lecture. Thank you very much for your kind attention and time. See you again in the next class. Okay, bye.